I'm Navin Dookeram, and a bit of background about myself. I did my undergraduate degree in petroleum geoscience at the University of the West Indies, and then I went on to do my master's in statistics. After that, I took up an internship at TSTT in data science along with Mariella and others. And we worked on a project involving the upselling of telecommunications products to corporate customers in the telecommunications sector. So my presentation today is entitled "The Recommender System for the Upselling of Telecommunications Products," and I collaborated with one of the employees there. She's a business analyst. Her name is Zahira Hussein, as well as Professor Patrick Hussein. So just to give an overview of what I'll be talking about today, I'll be outlining the details about upselling telecommunications products and why it poses a challenge. I will discuss the proposed solution, which is a recommender system that uses a logistic regression binary classifier associated with misclassification costs. I will then delve into the experimental model using data sourced from the telecommunications service provider. And finally, I will proceed to discuss some results obtained. So we consider upselling as a purchase of additional products and additional add-ons and/or the switch from legacy products to upgraded ones. Traditional methods of upselling rely on a semi-manual approach. So the company will assign an account manager to corporate customers, and each manager will meet with the customers on a scheduled basis to discuss their needs. And they will give any product offerings which could result in upsell opportunities. However, some account managers may not completely understand each customer's preferences, and this could lead to inappropriate recommendations. There's thus a greater chance for the semi-manual process to be time-consuming, subjective, and costly. So with our approach, we will be using data science and machine learning to kind of automate the process of recommending upsell products. And the data provided for this approach involved a host of variables. So we have basic customer demographic information, transaction data, and sales records concerning legacy products that the customer purchased. So here we would have things like the ID, the company name, the marketing sector, the company age and years, the industry classification, whether or not this corporate customer signed a VIP contract, the months until VIP expiration, the days since the last CIS installed, the number of CIS exchanges, and then different transactional information like the count of the brands of certain legacy products like PBXs or single lines or T1s or trunk lines, a list of all the legacy products, a percentage of these legacy products and the legacy rentals. And then we also have legacy minutes. And here I derive certain factors of whether or not the customer has these products or not, which is a binary factor. Then a count of the number of legacy products they have. And finally, these two important variables, whether or not the customer was approached for upsell and whether or not this upsell resulted in success, whether or not the customer engaged in the upsell or they turned down the upsell offer. So these two variables are the ones I will be using as target variables for the recommender system. Oops. So before model construction, feature selection was performed so as to utilize the most important features of the customer data, and this would maximize the model's predictive power. We computed a rank of the variables by assigning an importance value to each feature with the use of information gain. The top 5 features were found to be the most important with a positive information gain, while the information values for all other variables were computed to be 0. So these top 5 features are represented in this chart here. We have percent legacy products, percent legacy rental, percent legacy minutes, the last CIS install, which is the number of days since a CIS was last installed, and the number of legacy minutes that was a transaction between the corporate customer. So the procedure for recommending upsell customers was as follows. We have a set of corporate customers, and we divide them into 2 subsets, those who were approached for upsell and those who were not approached for upsell. With the approached subset, some customers would have had a successful engagement in upsell and others were unsuccessful. So these would represent our binary target variable. And we train and test a binary model on these to try to predict whether or not a customer who will be approached in the future will be successful or not. So this is historical data that is being used to train and test the model. We then apply this model on the unapproached data set. So these customers were not approached as yet, so we can't know for sure whether or not they will engage in upsell or not, but this could be used for future upsell engagement. And so we will end up getting results from the model where the model will recommend customers to target for upsell, and those will be left untargeted. So these untargeted customers will be ignored, and the targeted customers will be approached. However, we can then rank these targeted customers on the basis of how likely they will upsell to whether or not they would not as much upsell as we would like. So we can have a probabilistic model targeting the cream of the crop customers who will engage in the upsell. Now, initially, when our model is trained without incorporating cost, the resulting confusion matrix on the cross-validated training set was computed as shown in the left table. So this is going to minimize error or increase or maximize accuracy. So this gives an accuracy of 89.5%, where we add up the true negatives and true positives and divide by the total. However, there are many false positives. So we have 24 false positives and we have 36 false negatives. So this would negatively impact the telecommunications provider financially. The cost of a false positive, which is incorrectly predicting an upsell as successful, right? Incorrectly predicting an upsell as successful is much less than the cost of a false negative that is incorrectly predicting an upsell as unsuccessful. So why is this much less than, why is the cost of this false positive less than the cost of this false negative? Well, the cost of a false positive may only account for administrative costs. On the other hand, the cost of a false negative is the foregone benefit that would have been obtained if the customer was approached for upsell. And this benefit would be the revenue gained from the sale of the product. So in this case, with false negatives, we are missing out on sales, and hence we are not getting the revenue that we should have obtained if we actually did approach these people, these customers. So when applying cost weightings to the model, the number of false negatives is significantly reduced. So we see on the table to the right, we are not minimizing error here, but instead we are minimizing cost. And in reality of business, cost is probably a better metric to minimize rather than error, because we want to be revenue generating and we want to be, cost minimizing. So how do we calculate this cost metric? We come up with some metric called the expected cost of misclassification. So we say let Cij denote the cost of classifying an instance of class I as class J. We denote the PDF or the probability density function of the scores for class no instances by F0S, and for class yes scores by common F1S, right? we denote the corresponding cumulative distribution functions by capital F subscript 0s and capital F sub 1s. And the prior probability of class J belonging to class to no or yes is denoted by pi J. So the expected cost is going to be given by this formula here, where we take the cumulative density function multiplied by the prior probability times C00, and then we keep adding it on to each of the different metrics. So a necessary condition for minimizing the expected cost can be obtained, where F1T pi 1 is equal to F0T pi 0 into C01 minus C00 over C10 minus C11. And then we can obtain a threshold value T, which can be changed by varying eta. Eta is given by this thing here, C01 minus C00 over C10 minus C11. And the importance of having eta is going to be explained shortly, but we can see that this figure shows the performance of the cross-validated training data with cost optimal threshold in blue versus the default threshold in red. So the cost optimal threshold is when eta is equal to 0.1 and when eta is equal to 1, right? For eta is equal to 0.1, the cost optimal tune threshold value was T is equal to 0.0935 here, and the optimal expected cost was 0.2842, which is around this value here. However, there was a reduced accuracy of 76.3% when compared to the accuracy if no costs are implemented, which is 89.5%. Right. So obviously, if we were maximizing for accuracy, we would have gone with the red line. But since we are minimizing costs, we will go with eta equal 0.1. So in contrast, for eta equal 1, costs are ignored and the threshold T selected optimizes accuracy rather than cost, where the threshold T is equal to 0.50. The expected cost for the accuracy-based optimal result was found to be much higher with a value of 0.6737. So there's a trade-off, as you can see from the graph. If we maximize accuracy, we will not be minimizing cost. And if we optimize for cost, we will have to trade off with the accuracy. We evaluated costs using different values of eta. As we can see, we vary eta from 0 to 1 here. We then compare the cost of cost-based optimal result, C cost, with the cost of the accuracy-based optimal result, C accuracy. This comparison is achieved by calculating the ratio of two costs R, where the cost of the cost-based optimal result is the numerator. And in this figure, we plot the value of R for various values of eta. So when eta is 0, then the false positive errors do not cost anything, right? And therefore it is optimal to always choose the positive outcome, in which case R is equal to 0. And if eta is equal to 1, then this corresponds to unit costs for both types of errors, and hence this corresponds to unit costs for both types of errors, and hence the resulting optimal probabilities are the same that would be obtained for the accuracy. And hence, in this case, we get R is equal to 1. So we chose to display some results for varying values of eta. We selected eta equals 0 to eta equal 1. And from this table, we can confirm that as eta increases, the threshold T for optimizing cost also increases. Moreover, the accuracy of the model applied to both cross-validated training and test sets is also increased with increase in values of eta. So you can see an increase in accuracy from 0.69 to 0.89, and then the optimal accuracy is going to increase from 0.775 to 0.9, and this corresponds with eta increasing because an eta equal 1 means that we are optimizing for accuracy. Here we see that the cost optimals upsell cost the cost optimal upsell cost is always less than or equal to the accuracy optimal upsell cost for varying values of eta, which is an expected result. So it's always the cost optimal upsell cost will always be less than or equal to the accuracy optimal upsell cost. Now, one important thing to talk about is the success rate. So the success rate S increases as eta increases. So we see a value increase from 0.65 to 0.86. When the semi-manual method of approaching customers was employed, there was a total of 34 successful upsells out of a total of 80 customers approached. And this would give a ratio of 34 out of 80, which is 42.5% success rate. Hence, the utilization of a predictive logistic regression model to predict customer upsell for any given value of eta, be it from eta ranging from 0 to 1, dramatically improves the success rate that was achieved using the traditional semi-manual approach by at least 22.9%, because we go from 42.5% with the semi-manual approach to at least 65.4%. Right? The number of target customers selected for future approach for upsell is outlined in the last row here. We observe that this number decreases as eta increases, since the number of predicted outcomes is decreased. So the company can decide what value of eta to go with to minimize the cost. But also we want to have, to approach a lot of target customers. But keep in mind, the more target customers we approach, the success rate will decrease, right? So if we are selecting the cream of the crop, and we want to increase for accuracy, but not minimize for cost, then we could get a high success rate. But then is it to the financial benefit of the company to do so? We have to explore that trade-off, and the company will explore that trade-off. So in conclusion, we have demonstrated that upsell return can be optimized using a binary classifier with misclassification costs. Training and testing the model produced very good performance results. The model outperformed the current traditional approach used. And for future work, we can look at maximizing long-term profitability of upselling. And finally, we can recommend products within a defined future time window, for example, every quarter. So we have come to the end of my presentation. I wish to thank you for your time and attention. The floor is now open for any questions or comments you may have. Thank you.
Yeah, thanks, Navin. Any questions from anybody? Okay. I just want to point out a couple of things, so in both of these presentations, you see that we focus more on cost rather than accuracy. And a lot of the data science papers you will see, they provide accuracy results and other things like area under the curve, etc. But our feeling is, from a business point of view, you really want to minimize the overall cost. So which is why we focus on cost.